Hello everyone. Is Abdurrahim Babatunde Kukola. So you are all welcome to this video. On this video, I'm going to be instructing you on how to develop a gas membrane system modeling with Aspen Custom Modeler. So we are going to be going through the development process, and I'm going to be explaining the principle behind the software and the system, and how the software is very powerful for modeling system like that. So a gas membrane is system majorly like a water desalination or water like reverse osmosis membrane system that has been known for liquid separation. So it can be used for gas separation too. For example, when you have two mixtures of gas that you want to separate, so you can send to through a semi-permeable membrane that allows some component to pass through, while the rate of diffusion of some component is very low, while the rate of the like component gas is very low, while the other is very high. So with that, you can separate them by using high pressure pump that will create a pressure differential in between the membrane. So the membrane development, this is the background from some of the paper that I read in order to make this video. And the paper is actually developed by it's actually written by this person, Diana, and is titled Model Development for Gas Membrane Unit for Separation of Hydrogen and Carbon Dioxide. So I'll be using this paper and implementing it in Aspen Custom Modeler. So, and the flow sheet for most of the system is actually a continuous flow system that you have a membrane separation like a pressure unit. Then you have the feed that is flow through the one side of the membrane. Then as the flow is, you can have a countercurrent or use a co-current arrangement. Then you have a strip gas to strip off the permeate or diffuse gas through the membrane. So in the remaining gas is now taken as retentant, and then you can have multiple stages that are connected together in order to increase the efficiency of the whole process. So for the process, like I said, there are different configurations. You have the concurrent setup, you have the countercurrent setup, where you have the concurrent is you have the feed going in one direction, and the permit is also taken in the same direction. While for the countercurrent, the permit is going in the opposite direction. Then you have the perfect mixing and perfect mixing setup. So if you read some other book, you can see some places where you have compression and vacuums. Vacuums can aid flow. It depends on the diffusivity of the gas and the kind of setup that you need to do. For example, if the diffusivity does not support the pressure you, as you're operating the system, the gas does not diffuse very at a certain pressure, so you have to consider those kind of pressure or diffusivity of the gas that you're trying to separate and the type of membrane that you are using. Then you have this one, a permeate dilution by strip flow. So this is the one that I showed before. Then you have a recycled for retentate, so that to ensure most of the permeate is actually separated. So, and you have different configuration that you can have for the system. So, basically the technology is actually using a membrane, that's semi-permeable membrane, that allows some gas to pass through, while some gas molecules are actually hindered from passing through the separation layer. Then you have your permeate gas and this, and it's mostly aid with the pressure and high pressure or pressure differential in between the membrane. So so the membrane can be you can see the layer of the membrane. You have the spacer, multiple membrane, retentate is flowing through the side of the membrane, then the gas is diffusing through the membrane. Then you have it in 3D form, the schematics, different layer of the membrane sending, then you have the retentate flow, then the duct for the permeate flow inside. It's good to design this kind of shape instead of having a rectangular or some kind of plate design. It's good to use the circular design to economize space and the likes. Then you have the packing density. This is a spiral wood. This is a tubular design and capillary model, stuff like that. So, but that's not majorly our own concern in this video. So for designing the system, there are some kind of theories like chemical engineering theories that have been developed for the model through Fick's law, and those are the things that we are going to be implementing inside the code, inside the model, more rigorous model for the system. So like I said in some of my previous videos, the Aspen Custom Modeler is very useful for modeling complex system, and it has the it is very flexible, and you can easily customize your model in any way that you want because it uses basic fundamental mathematical equation that we all started chemical engineering with. So, and some of the guiding theory for the membrane separation is all this equation that is written there. So you have the flux. The J is the flux given in terms of the chemical potential and the length of the membrane. Then you have some other formulas that have been given. Then it is expressed as this in Fick's law. Everything is expressed, it is summarized into Fick's law, which is diffusivity, then dc. Then when you integrate Fick's law, you get this formula for the membrane operation. Then you can also convert the Fick's law from concentration base to partial pressure base using this function. So that's basically what this section is explaining, like interpreting the way you can solve the problem. Because if you are using condensation, it might be difficult for some people, you understand, or you might not really be interested in measuring the condensation, but the pressure, that's what you want to measure. So that's another thing. Then you have the permeability coefficient and the stuff that you can now fit into equation to get what you are trying to do, as you have seen from here. So this formula, you can now get a model for that represent the pressure and the flux, the rate of flow rate per unit area of the membrane surface. So flow rate of the permeate gas per unit area of the membrane surface. So you know the rate at which each of the gas is moving, is diffusing through the membrane. So from there you can do some simulation or adjustment of the model. So with these basic theoretical equations, we can develop server model for it, like in Aspen Plus. There are some other models that you can use in Aspen Plus, like the Excel function. If you use the Excel user model, you can develop the model, but for flexibility, and I prefer to use Aspen Custom Modeler, you understand, than, because to set up the Excel model takes a lot of time, and you can use Fortran code if you also have the luxury of the but it's actually, for me, those kind of model is not the right path or the right approach. It's better to use Aspen Custom Modeler, which is simpler and more easy to use. The code is not very hard to learn, and the solver is also good, and there is a lot of solver, non-linear and linear solver in the software. So just interpret the mathematical equation, and you get your code. So for the formula, we have to do some modification. There are some models that have been developed in this paper. you have the first one, which is a very simple approach using the feed flow rate. This is material flow. Like you said, you have the feed flow, the mole fraction of the feed, then the retentate, the mole fraction of the retentate of each of the gas in the retentate. Then you have the permeate, then the flow and the mole fraction of the permeate. Then the flux is given in terms of the flow of the permeate and the mole fraction and the area. Then you have another function, because flux times area, that will give you molar flow rate. You understand? This area flux, the molar flow rate, flow per area per time. So then you have this diffusivity rate of flux, which is given in terms of these equations too. So these are the four basic equations for the first model. And for the second model, which is the one that we are going to be doing, is actually a distributed model, that you have y is equal to k minus 1, f is equal to k minus 1, yk, fk minus 1, yk minus 1. So this is actually based on creating a subunit for each area of the membrane and doing material and energy balance for them. And then we have the flux that is calculated for the first simplified, that you take the whole lump of the membrane as one unit, that is now done for each of the subunit of the membrane. And then you have this third model, which is actually based on distribution equation and with respect to x, and some kind of more rigorous approach to the modeling. So for the code, we are going to, in order to create the model, implement the model in Aspen Custom Modeler, we are going to first set up the component list. So I'm going to add the component list as okay, this one is when you are trying to create a new component list from Aspen properties. So there are three components. I'm going to write H2, CO2, and N2. Then for the I'm going to select Penck-Robinson equation of states for my property model. So let me just search Penck-Robinson for my property model. Then I'm going to estimate all the retrieve all the parameters from the data bank. So I think everything is set now, so I can save the property file for the model. So to save it and close it. So this is the return after it has, you can see, configured using embedded Aspen properties. So then we can go to default and select, I'm going to just select hydrogen and CO2 as my components. Then you can see the property of the main system and everything given here. So then after doing this, the next thing is to create my model, my membrane model. So I'm going to call it membrane, or let me call it membrane. Okay, let's call it gas membrane. Gas membrane model. Gas membrane model. So you can see the basic equation for the gas membrane. We have the parameters, the variable values, and the submodels and the likes. So I have to create some of the equations that we are going to be using in the model, like the flow, the how will I call it, because I'm trying to do the second model. So we have to create some of the variables that are going to be using in the equations and the parameter that will be useful for the model. So for the variables and parameters, I created numbers of cells, which is numbers of division, numbers of these subunits that we have in the membrane. Then I have area, I have L mole, which is for this one is the permeability of the gas through the membrane. Then this permeability will be converted to molar permeability, because the standard unit for the permeability is often given in meter cube in volume basis. So we use the ideal gas law to convert it into molar basis. Then you have the ppam, that is the permeate pressure, that is the pressure of the the pressure of the permeate side of the membrane, and it's given in this formula. You can see the permeate pressure ppam, so it is needed in the code. So then we have the areas of the cells, that is area of each of the flow cell that we divided into the total membrane. So this is the total area of the membrane. Then you have the flow of the retentate, the flow of the permeate, the mole fraction of the retentate, the mole fraction of the permeate with respect to this is from the initial north, this is the north side, then the final flow. So as the flow is going, we are going to be getting the increase in the flow. Then the flux from the first cell to the last, you understand. Then the mole fraction is also given. So F naught is the initial flow, that's why this is starting from 0, why this is starting from 1. Then you have the density. The density will be very useful, you understand, but it is the reason why I put it in air is not going to be shown in the model fonts. Is going to be inside the code as a source code or something. So you have this one, it doesn't have a type, variable type or logs. It's just it's a form of type. So no type is like a system variable type, parameter type. So this is the parameters and the variables that I'll be using in the code. The next thing is to define the ports, the inlet and outlet ports of the model that will be coming through the model and leaving the port. So we have to define the ports of the retentate that is living in the beginning of the cells, that is this side of the cell. So that's the retentate flow in, and the permit in case you are using a sweep gas for your model, so that the model will be flexible to use. Then the outlets of the total cells, the ending cell, which is the retentate flow out and the permit flow out. So these two need to be defined. So you can see the ports. This is okay, this one I will explain this later. So the inlet is inlet port, mole fraction port. Then you have this input, this is output. This is retentate port, the name I gave to the port: inlet, sweep, retentate, and the permit. So we start writing the equation. As I said, we need to convert the permeability to molar basis from this label that you have. So you have the basis given, L basis given, or if you have the L mole basis, you can specify this, then you calculate this L other one, because the software has the capability of reverse calculation. It doesn't follow a certain format. That's one of the powers of the Aspen Custom Modeler software. So you have this is the standard pressure, standard temperature, then the universal gas constant, then this is for conversion of the units. You understand? The 1000 is for conversion of the unit. So you have the formula from the ideal gas law. So in case if it is actually you want to do it better, you can use the equation of state to calculate it. So but then you add the compressibility, you understand, to the gas or something. So but this is good enough for this level. Then you have the retentate inlet connection. So like I said, the flow in, which is for cell naught, the north cell, is given as the inlet flow from the ports and the sweep gas flow. For the remaining part of the code, you have this for the mole fraction in the inlet port. You have Z retentate for each component in the component list. The component list is the list of the components that you defined. You give me a minute. The list of the components that you defined. Let me show you the component list. The component list is the list for the component that you defined there. All the component that is in this default list, that's the component list. So it's going to it's like a set of properties that is going to calculate for them for the for each of the components. So when you define them in the model, this is where you open the code editor. So when you define them in the model, you have it here, the retentate inlet flow, the mole fraction. So the component list is now given as Z retentate comp 0, Z permit comp 0, the inlet flow rate. Then you have the equation, the areas of cell, the total area of the cell, the area of each of these units of the cell, the flow channel inside the cell is equal to A divided by numbers of flow channel that you have in the cells. So dividing the area into subunits, like you have all this area of this small cell, area of these other small cells. So and then you have the flow of retentate. This is the material balance equation. This equation, as you see, is the same thing as what is written here the first time, which is Fk minus 1 is equal to Fk permit minus 1. This is like total flow in each of the cells. Total flow in this cell is this flowing plus this flowing was equal to this flowing and this flowing as given in this place. So minus 1 is the one that is leaving the preceding cell and going to this current cell. Then you have the component material balance for each of the components in each of the cell. Then you have the flux formula for it. As you can see here, this is the total material flow. This is the flux formula. You have area of the cell, L mole, then the pressure, the inlet pressure, because pressure is actually constant. So you have there is no pressure drop model in the model. So if you want to include pressure drop configuration, you can add it in the code and easily customizable, and you see the influence on the system modeling. So then you have the log, the lane, the log E. Then these are those to reduce the error in the division when the code is running. So then you have the retentate pressure, the permit pressure, and the formula given here. Then you have the F retentate, Z retentate. This is for the component material balance. So it's under a for loop operation. The meaning of for loop is to loop. It will be counting from 1 till numbers of cells. It will be replacing all these index with 1. That is when F retentate is 0. Then till when the value is equal to the numbers of cells that you specified in the model. So it's actually parametrics. You understand? So then you have the comp in component list. So for all the component list, it's still going to do for all of them. So the numbers of components that you define is going to loop them through this code and generate equations that will be solved. Then you have another one. The summation of the mole fraction of the component in the permit must be equal to the one that is calculating. So it's another form of equation that binds the whole solution so that it is it is not over specified or under specified. You understand? So then we have the ending connection. The permit flow will be equal to F permit numbers of cell. Then the permit flow mole fraction will be equal to the end mole fraction and the flow times numbers of cell. So these are another formula for component material balance at the end of the cells to transfer the information that is calculated to the port, to the outlet ports, so that it can be calculated. Then you have the outlet connection, other outlet connection. You have the retentate temperature. That's the constant temperature. So if you want to do energy balance we can do energy balance. And if you want to assume isothermal condition, we can assume. So currently we are assuming isothermal condition. We have the retentive pressure, inlet pressure, the primary temperature, the strip gas temperature. The primary pressure is equal to the strip gas pressure. That is a isobaric condition too. So then these are the subroutine to calculate some outlet property like the enthalpy. So this one is to call the enthalpy. Then this one to call the density. So from it we can calculate the molar volume of the outlet stream that is leaving the gas membrane system. And that's the end of the code. So after writing the code that is given in this form, you can now compile for any error. So if there's any error, you are going to see a warning in the message. Where's the message tab? In the message tab. And since there's no error, so you can continue. So after compilation, the code will be done. So we can add the icon as it is given in this place, the icon for the gas membrane system as it is given like this in Aspen Custom Modeler. One of the advantages of using the software is you can create your own icon for the model that you created. So I'm going to be showing you how to do that. So to hide the icon, we can draw it from basic shape like this. You see the basic shape. Then I'm going to create another one inside. Okay. So I have created another one inside. So I'm going to be creating some lines inside it. I'm going to be creating some lines inside it, so that I'm going to be duplicating. So the next thing is to add the ports in the system. I'll add the ports there, the permits, the retentate. I don't know if this one is a inlet. This is supposed to be the inlet port. Okay, we can go back. I think it will save. So we can save the icon. So the icon has been saved. Then we need to add some forms too for some variables that will be calculated in the model. Okay, before we do that, let's create the model. So we can create the model in Aspen Plus. This is the model like this in Aspen Custom Modeler. Then connect the port. So I'm going to be connecting the port. So I'm going to be connecting the port. So we have two inlet stream. This is our permits. I'm going to be renaming them. This is the inlet. So we have all these streams defined for the system. So for the flows, let's do it like this. Let's specify 20 kilomole per hour, because the feed side, the retentive side, should have a greater pressure. So I'm going to specify 7 bar for the retentive pressure, the temperature to be 35 degrees Celsius, while the feed gas composition is 0.3 CO2 and 0.7 the other one. And I'm going to be fixing the variable, all these variables. I'm going to be fixing all the inlets, my specification. add this one too. So we fix everything. So these two, we fix this one too. So we fix this one too. So for the gas membrane system, we can add for the area can be 20 meter total area. It will calculate the cell area, but what is actually so important is the compressibility. Compressibility has to be calculated. I think I got the reference from this paper. Yeah, this is the variable. I think it's not here. I got it somewhere. Okay, I see. This is for methane and something. This is for methane. I got the reference from somewhere. So the compressibility is for the CO2 is 6.6457. 6.6457. While that of the hydrogen is 1.99734. Can search for it online using. Then numbers of cells is division, let's say 10. When you change it, it will change. When you change it to 5, you see the whole system will change. So it is parametric. So I'm going to make it to be 10. Where is this? I'm going to make it to be 10. So it is now 10. So and you can see numbers of variables to specify has been done. So your specification is correct. So before I run the model, I am going to I forgot to specify this one. So let's say the sweep gas is 0 at the pressure has to be lower than like 10% of the feed pressure, same temperature, then no CO2, then pure hydrogen as the outlet for the permit. Then I can run the model. Okay, I think it's good. So you can see the results from the model. The permit flow and the retentive flow is not really much. Then the flow rate outlet. Then we can see the results here, 0.5, 0.4. While for this, we have 0.7, hydrogen 0.2. Then for this, we have 0.37. So for getting the model right, we can still create like a profile plot for the profile of the variable of interest. So I'm going to create a results plot for the variable of interest, which is based on the profile for the amount of the gas that that permeates through the membrane. So I'm going to be creating some profile like F palm. This will contain the variable. This will contain the variable F palm or the variable of F palm. Then I'm going to create another one, Z palm H2 for hydrogen. So this will contain the variable of the mole fraction of hydrogen that permeates through the membrane. Let me copy this. Then we have another one, Z palm CO2 for the CO2 amount of component that permeates through the CO2. So we just change this one to CO2. Z palm CO2. Then we can plot all these in the profile plot. We apply it, then we make it okay. So you can make this profile icon to be the default form of the icon by saying make default. So it's going to be the default form of the icon. Then we are going of the model. Then we are going to compile it to implement it. Then we can run, and once you double click on the icon, you see the profile plot. So this is the result. So the mole fraction is given initially and finally, then the other flow is increasing with respect to the length of the profile plot. And we can add some of the variables to see it better. Maybe for example, we add the flow, and we just plot this. We add the flow. You can see the two mole fraction is given with increasing and decreasing mole fraction. So then for the other one, we can show this, but add these two and see the only plot for the flow, and we can also see the value in the table. You can copy it and please put it in another data or analysis software. So that is the result of our gas membrane system modeling with Aspen Custom Modeler. We are able to simulate the flow, the permeability, the permeation of the hydrogen through the membrane by specifying their permeability, experimental measured permeability through the membrane. Then with this model, we can design different gas membrane system based on the configuration, the pressure requirements, and see the difference between the relation between the pressure differential on the purity level, on the performance of the system. So stay tuned to us to get more exclusive video of this type in Nubia Process Designers. And if you request any assistance in your design project, or your chemical engineering design, your simulation analysis, or research development of your chemical system, petroleum system, you can always send us an email on our email address, numbera@gmail.com. So thank you for your time. Stay tuned.